L minus 1 over mn sigma j from 0 to k nj. That's right. We substitute this formula columns. For example, is T R0 is this item is the same for all of us. Okay, for all of the items from 0 to 7. L minus 1 over mn is 7 over, for example, 64 by 64 is 4k. Okay, 4096. This is the same for all of them. But here, sigma from 0 to 0 nj is only 790. That's right. Multiplied by this item is, for example, 1.33. Okay, SA1 is a transfer function of R1. Okay, again this scalar. Here sigma from 0 to 1 nj. That means 790 plus by 1023. That's right. This is another one, 3.8, and all of them. S2 is, for example, 4.55. Okay, and S3 to S7. S7 is 7, as we, for example, regarded. That's right. Go to the next slide. Here, by rounding to the nearest integer, okay, rounding, we see that S0 was 1.331. S1 3.8 rounds to 3. S2 from 4.55 to 5. Okay, and S3 from this item 5.6. Okay, for example, to 6, and 6 others to 6. S5 6 others to 7, 6.65. Okay, to 7, and 6.8. Okay, to 7, and 7 to 7. That's right. You see here, not. We see our S's here. Okay, but here the histogram of the new variable is found as follows. P0. Here you see it is S0 to 1. Okay, we don't see any 0, and after 1 you see 3. We don't see 2. Okay, after 3 we see 5. We don't see any 4. That's right. That means the probability of existence of 4 is 0. The probability of existence of 0 is 0. For 2, the same. PDF of 2 is 0. That's right. Here, P0 is 0. For example, P2 is 0. Why? Because any of the S's, SI's isn't 2. 1, 3, 5. Here you see SF4 is 0. That's right. After this nearest selection. Okay. But P1 here is 1. How many ones is here? Okay, P1 is here. P1 is PS0, and P0 S0 is PR0. And what about PR0 is here? PR0 is .19. P1 is PS0, we said it. P2, there isn't any 2 here. Okay, thus P2 is 0. But P3, okay, what is 3 here? 3 is for S1. Okay, P3 is PS1 or PR1 in this table. Okay, or PR1 is .25. Again, P4 is 0 from here, and P5 5 is here. P5 is only 1 5. Okay, is for PS2. PS2 is PR2 in this table, and PR2 is .21. But here P6. Okay, you see here S3 is 6. okay, result 6, and SF4 result 6. Okay, that means PS6 is PS3 plus by PS4. That means is equal by PR3 plus PR4 in this table. Okay, and summing these two items, 3 and 4, these two items, 3 and 4, 0.16 and 0.8 means 0.24. That's right. And PS7, 3 items here, 4 SF5, 4 SF6, and 4 SF7. Okay, that means PS7 is PS5 plus by PS6 plus by PS7, or in this table PR1 plus by PS for original image. Okay, PR1 plus by PR6 and plus by PR7, and summing these 3 items, 6 plus by 3 is 9, plus by 2 is 11. Okay, but in lower resolution is 0.1 only. That's right. Or certainly is 0.11. 0.11. That's right. Go to the next slide. This is the 10 near to 11. Here, for that example, okay, you see here the figures for histogram. Refer to the following figures for original histogram. This is the histogram for first one, okay, original histogram, and transfer function and new histogram. This is the transfer function, okay, TR, resulting from RAK to SAK, okay, and this is the resultant. Here is PR, this is PS, PRRK, PS, SAK. You see the histogram is so flattened, not fully, okay, some flattened and some not extended but flattened, okay, some flattened. You see here illustration of histogram equalization of a 3-bit or 8 intensity levels image. A, original histogram, this item, B, TR or transfer function, and C, equalized histogram. That's right. And go to the next slide. Some discussions. Due to discretization, the resulting histogram will rarely be perfectly flat. Okay, we said in previous sections that not totally flat. Some items flatter, okay, not total flat. And you see here this item compared to this item, okay. However, it will more extended compared to the original histogram, we said in the previous cases and previous session. That's right. Another discussion and another thing. A set of images with some content but with some different histograms, okay. With same content, with same content but with different histograms. For example, this figure here, the first one, dark image, okay, and you see this is dark image located about the 0 intensities, okay. B or 2, bright image here, and you see about the histogram. The histogram bars are located, for example, about 255, okay, for high intensities, located here. These 2 items, low contrast and high contrast. You see here, this is a low contrast image and this is a high contrast image. In the low contrast image, you see the histogram is located or compacted, okay, and in the high contrast, you see that the histogram is expanded, okay, very expanded compared to the above figure. Go for some discussions. For example, the first one, histogram equalization. First histogram equalization applied to the dark image. This was the dark image, and this was the its histogram after equalization. Okay, you see in the last slides, after equalization, this is the histogram, flatter, okay, flatter and more extended, okay, compared to this item. And this is the resultant image. The resultant image is very better than the original one, okay. This is for the first example, for the dark image after equalization. This histogram equalization tends to improvement, okay, or better performance for the image. Next slide. For bright image, you see this image and its histogram located in the higher intensities, okay. After equalization, you see again extension from 0 to high intensities, okay, and more flatness, okay, compared to the original. And this is the resultant image. The resultant image is very better than the original one. Again, the equalization for the bright image, okay, dark image here, bright image, and go for the next item, low and high contrast images, okay. This is for a low contrast and this is for a high contrast. And after applying the equalization, you see the resultant items are both of them better, okay, and for example the same or equal each other, okay, starting from low contrast and high contrast, we see the same, for example, resultant image. And this is the resultant histograms, okay, for 3 and 4. This is the original one. The original one for low contrast. This is for the low contrast, and this is for the high contrast, okay. That's right. Go to the next slide. Here, a good slide. Transformation functions for histogram equalization, okay, for the previous example, for dark, for bright, for low contrast, and for high contrast. We see all of these 4 items, okay, in this only figure. You see the function TR used to equalize the 4 images for the previous example is shown below, okay. Observe that the transfer function in cases 1 to 3, 1 is 1 for dark, 2 for bright, and 3 for low contrast, okay. Here you see 1 you see here is in the dark intensities, okay, the field of activation, for example about 0 intensities, okay. For 2 is for bright, here is for 2. Why? Because the original image has an histogram in these areas, okay, in the higher intensities. For 3, let's see here, you see 3. Why this sharp, for example, slope? Why? Because we had a low contrast, okay, image, and a located and compacted histogram, okay, and you see the equalization transfer function has a high slope, okay, and the 4-1 is for a high contrast. High contrast itself has a expanded histogram, okay, and you see the equalization function is expanded to from about 0 to about 255, full range. That's right. Again, I read from here. Observe that the transformation function in the parentheses for equalization, okay, in cases 1 to 3 maps the small range of intensities to the entire range of intensities. Okay, this small range to a full range, for example, from 0 to 1, okay, or to 100%. Observe that for an image which is already bright, the transformation is an almost diagonal line. Okay, this item 4, not bright, not already bright. This is wrong. For an image of high contrast, not already bright. Okay, for an image of full contrast, you see that this 4 item, you see that the transformation is an almost diagonal from 00 to 255, or 255, 1, okay, or 100%. That's right. Go to the next slide. Okay, it was complete. Another discussion and another subject, histogram specification. Okay, we want to go, for example, design and change the histogram of an original image to a specified histogram. Okay, for example, you see a special histogram and want to change your original histogram to this new one. This is this subject. Histogram specification. Okay, we are looking for a technique which can provide an image with any pre-specified or specified histogram. Okay, this is called histogram specification. We assume that the original image has, for example, PDF PRR. Okay, we are looking for a transformation Z is TR, which provides an image with a specified PDF PZZ. Okay, this is a specified histogram. Histogram specification uses histogram equalization, okay, the last subject, as an intermediate step. We see in these slides. Okay, First, equalize the given image with PDF PRR. For example, S, the resultant, is TR. We had this item, okay, in last sessions. Is L-1 dot integral of from 0 to R PRW dW, for example. Okay, this is the meaning of CDF. Okay, cumulative distribution function. Okay, for S, for resultant pixels. Okay, if you had the desired image with PDF PZZ, for example, we could equalize it and obtain S is GZ. Okay, S is GZ. S is the output histogram. Okay, S is GZ and is again L-1 dot integral from 0 to Z PZZ DZ or PZW DW is the same. Okay, based on the above, we can assume that GZ is TR. Okay, thus Z is G inverse TR. Okay, we need Z and PZZ. Okay, what is Z? Z is G inverse TR. Okay, TR was S. Okay, G inverse S is Z. In the case of continuous variables, if PRR and PZZ are given, we can obtain Z after formulating the function T or G inverse. Okay, for example, continuous. But in discrete case, okay, in the discrete case, we firstly equalize the initial histogram of the image. First equalizing. SK is TRK in discrete and is L-1 sigma J from 0 to K PR R or PR RJ here. Okay, and referring to formula of PR, okay, is NAJ divided by the total, means L-1 divided by M dot N dot sigma the sigma of n rj, not p rj. Okay, that means sigma from j from 0 to k n rj. With n rj, the number of pixels with intensity rj. Okay, for example, n r1, how many pixels have r1? Okay, or how many pixels have r2, etc. r2 intensities in the last for example table, r0 to r7 for example. Then we equalize the target histogram. sk is jzk and is l-1 sigma pzzi. Okay, pzzi from 0 to k for example, and is again l-1 or mn sigma nzi. With nzi, the number of pixels with intensity zi. And finally, we try to obtain some type of inverse transform. That means zk is j inverse of sk or j inverse of trk. What we said in the last slide. Okay. Maybe some example. This is a numerical example, and this is very good. Histogram specification. Previous example, for example, total number of pixels 64 by 64 is 4096. Okay. Here is the original histogram. Okay, and here is the desired histogram. For example, we want to change from this histogram to this histogram. Okay, and we have the number of all of them, and we have the formula of both of them, the original and the desired. Here is this table is for the original one, original intensities. Okay, for example, R0, this axis is for R. Okay, this is for R and this is for S. No, not for S. This is a P. This is PDF. Okay, probability density function. But this item I is R. Okay, R0, R1, R2, etc. R's, and these are the PDFs for each R's. Okay, that's right. 0, 1, 2. Original intensities, intensity 0, intensity 1, 2 to 7. Okay, the number of pixels, for example, we had from that table, R0 has a number of 790. Okay, for example, R1 1023, and etc. This is the probability, the third column. Okay, for example, for R0, this is the NK and this is the PK. Okay, here you see the PK. For example, dot 19. Second one dot 25, dot 21, etc. Okay, this is the CDF. Okay, cumulative probability, or CAM or CDF. Okay, each of item is summed by the previous items. The first one is 0.90. The second one is the sum of 0.25 with 0.19. Okay, that means is 0.44. Okay, and etc. The third one is more and more, and the last item is 100%. Okay, or 1. In CDF, the last item is 100% or 1. The next item, the equalized intensities, or CAM plus multiplied by 7. Okay, that means, for example, here 1.33, 3.8, and etc. And the last item as we had regarded is 1 multiplied by 7 is 7. And after normalizing, okay, for example, 1.33 is normalized to 1. 3.8 is normalized to 3.08. okay, is normalized to 3, and etc. 1, 3, 5, 6, 6, 7, 7, 7. Okay, this is for all of these items. All of these items in this slide is for the original histogram. Okay, not the resultant one this time. Go to the next slide for starting for the resultant item. Here, these numbers of rows are for example, R0, R1, R2 to R7. Okay, original intensities. These are equalized intensities that are available from the first image, okay, or from the normalized CDF of the original image, as we saw in the last item of the last session, that last slide. We see no. Where is it? Here in this item. Okay, you see 1, 3, 5, 6, 6, 5, 5, 5. I jumped by slide. Here, this slide is for desired intensities. Okay, this slide was a jump version, but I go back. 38 is okay. We had the last slide 37 for the original histogram. Okay, and after it the CM, after it the normalized CM or normalized CDF, and here is the normalized CDF. Okay, but here the same mathematics for the desired histogram. For example, R0 to R1 to R7, and probability. You see here from this desired curve, you see 0, 0, 0%. That means for R0, R1, and R2, the PDF is 0. That's right. From this figure, okay, PDF for R3 is 0.15. Okay, for R3 is 0.15. Here for 4 is 0.2. Okay, or 20, and other items for 5, 6, and 5, 0.3, 0.2, and again 15. Okay, 3, 2, 15. This is for CDF. Okay, 0 plus by 0 is 0, 0 plus by 0 is 0, 0.15 plus by 0 is 0.15, 0.2 plus by 0.15 is 0.35, okay, and etc. This CDF. This is equalized CDF, okay, or CM.7, 000, here 1 point some items to 7. Okay, and this is the normalized to the nearest, for example, the nearest natural number. Okay, 0 to 0, 0 to 0, 0 to 0, 1.05 is 1. Okay, and other items. The resultant is normalized is 1, 0, 0, 0, 1, 2, 5, 6, 5. Okay, this is the resultant normalized CDF. Okay, for the resultant desired histogram. Okay, and go to the next slide. Here is original intensities, and here is original equalized intensities, and that is available from the original image. Okay, you see the items. We had it 1, 3, 5, 6, 6, 5, 5, 7, 7, 7. Here, maybe from slide here slide 37. Okay, here this item. Normalize CDFs 1, 3, 5, 6, 6 and 3, 7, 7, 7, 7. You see here, this is the available normalized CDF. Okay, 1, 1, 1, 3, 1, 5, 2, 6 and 3, 7. This item no, and this item, the desired intensities. Okay, from the slide 38. This item 0, 0, 0, 1, 2, 5, 6, 7. Okay, or not? No. Oh, okay, here 0, 0, 0, 1, 2, 5, 6, 7. Okay, this is not available. We are banning it. Okay, this was available from the original and we ban this item. Okay. Oh, okay, we are banning going from here. This is duplicated of this column. This column is duplicated of this column. Okay, available. We want to go from, for example, 1, 3, 5, 6, 6, 7, 7, 7 to this desired. Okay, to go to 0, 0, 0, 1, 2, 5, 6, 7. Okay, going from this 1 to 0 is forbidden. Okay, why? Because PDF isn't negative. Okay, all of times. That means we can't go from 1 to 0. Okay, this is the same for these 3 items. But the first one, I can go from 1 to 1. Okay, 1 to 1 here this time. Okay, what about the desired intensities? The desired intensities is here for R3. Okay, 0, 1, 2 is all of them is 0. Okay, and R3 is this match 1 to 1. Okay, and go here for 1 to 1. I tap here in new intensities 3. This is R3 for new, for example, image. Okay, and continue from 3 to 2. Okay, what is the row? This is the row 4. Okay, that means 3 is mapped to 4. 3 is mapped to 4. Again, from 5 to 5 is row, for example, 5. That means 5 go to 5, 6 and 6, both of them. Okay, 6 and 6 go to 6. Okay, 6 is the same as 6, and the 6 is in row 6. Okay, that means these 2 items is mapped to 6. 6 and 6 is mapped to 6 and 6. 7, 7, 7 is mapped to 7, and that is in the row R7. Okay, and all of these items is mapped to 7, 7, 7. This is the resultant new intensities. Okay, and here this is available. Okay, 3, 5, 3, 4, 5, 6, 6, 7, 7, 7. Okay, that's right. This isn't good, and this isn't the wrong. Here you see the wrong pictures. Okay, notice that due to this discretization, the resulting histogram here will really be exactly the same as the desired histogram when we said it. Here, this is the original histogram. This is the desired histogram. Okay, and this is the constructed histogram. Okay, is maybe or nearly the same as the desired, not exactly it, okay, this is the nearest one, for example, to the desired item. This was original and this was desired, and this is the resultant, okay, constructed. And this is the CDF, okay, that's right. This was for reaching to a desired histogram from a, for example, original histogram by this, for example, 3 slides. For example, this picture, and this is the, for example, maybe some darks, okay, some items here and some items here. These items here in the histogram are for this area, okay, only, and these items, okay, we see two items, 2 areas. One area is here, okay, and one area is here. Okay. This area is for about here, for example, here, and this area is for all of these items, okay, this fields, all of these items. Go to the next slide. This was the original, okay, but here transformation function for histogram equalization, okay, for example, this TR for equalization. We reach from the last histogram, from this histogram, okay, with using with this TR to this resultant in the histogram, okay, and you see the resultant image. Because of this form, from this area to this area, maybe all of the range, okay, you see the contrast is very damped, okay, contrast is very worse, not better. But here for enhancing, okay, as we said, again, this is a specified histogram. For example, okay, B transfer functions, for example, 2 transfer functions, transfer function 1 and transfer function 2, okay, 3 here, 3 enhance image, this is 3, this is C, okay, as here, A, B, this is C, and this is D, okay. This is enhanced image using mappings from curve 2, okay, okay, and this item, the resultant histogram compared to, for example, this histogram, this was the original histogram, okay, this range and this range, but the resultant here is gone to brighter area, okay, has gone to the brighter area, and you see it, and these fields, okay, are flatter, okay, from, for example, about 180 to 255, it's flattened in this item. This is okay. Go to the next slide. Okay. Another example, only example, and the formulas are the same. This is the original image, and this is the resultant. I read it: image after histogram modification. Okay. And this is the original histogram. This is the specified histogram. Okay, we want it specified histogram, and histogram attained on modification. After modification, you see the resultant is nearly the same as this desired. Okay, nearly the same as the result and as the desired. Okay, and you see the images. That's right. That's object was completed, and we see another subject. Okay, another subject in the histogram. excuse me, local histogram equalization. Local histogram equalization. To this time we was discussing about global equalization. All of our pixels of an image, okay, an original image. But this time, in some situations, for example, you need to improve the top corner, for example, of left of an image, okay, and don't change other areas, or don't care, okay, but that corner is very important for you, okay, and you zoom over that histogram, that area, that local area's histogram, and are attempting to improving that histogram, okay. In this slide, in many cases, histograms are needed for local areas of an image, okay. Possible applications, for example, could be pattern detection based on histogram, adaptive enhancement based on histogram, adaptive thresholding, object tracking, okay, all of these items based on histogram. You see in this picture, for example, you see an scene in, for example, a park, okay. This item is maybe some items, this is another item, and this is another item. But in these three items, maybe this is more important for you, the stop flag, okay. You see this port or this area has this histogram, this important area has this histogram, and this, for example, scene has this histogram. But you see the resultant one is the same as the more important one, okay. The more important, that is for stop, okay, for stop table is selected, and the target histogram is the same as it. Okay, you can change the all of histogram globally to this item, or you can select areas and change the histogram of each area as the desired or target items, okay. Go to next slide and discuss more. Here, local histogram equalization for local image enhancement. The histogram processing methods discussed previously are global, okay, and act globally. Transformation based on the intensity distribution of the entire image. Okay. This global approach is suitable for overall enhancement, okay, not for a specific area. There are cases in which it's necessary to enhance details over small areas in an image, as for example that stop flag, okay. The number of pixels in these areas, important areas, okay, in these areas may have negligible influence on the computation of a global transformation. That means global transformation isn't good, okay, because the number of the small number of these pixels in that area. The solution is to devise transformation functions based on the intensity distribution in a neighborhood around every pixel, okay. This area, etc. The above approach facilitates tasks such as detection, tracking, and especially adaptive thresholding, okay. As said, you see a good example here. Example, local histogram equalization. For example, you see the original one, okay. In this image, you see a low contrast image from the Mars, for example, low contrast, and you see the resultant, the corresponding histogram, okay. For example, very compacted bars in histogram, and this is the red one is the equalization, okay, one. Here, the second one, you see the using the global equalization, Okay, this is better than the first one, but is using from the global equalization. Okay, but in the third one, you see is very better. Okay, from the second one. Why? Because you use the local improving or local equalizing the histogram. You see, this area is very clearest, okay, very more clear, okay, than the second one. Or for example, these items, all of them, okay, because we divided all of the picture to smaller areas, and each area is using the local equalizing, okay. This quality is very better than the second one. And you see here you see, for example, you see flatter, okay, flatter than the first one, okay, and some extended and some brighter, okay, but not all of these items. But in this third one, you see more flat, okay, more flat than the second one. And you see, for example, more extended from 0 to the 55, okay. And this is the red one, this is the equalization one. It's very better and very linear, and from this is diagonal, okay. For example, from 0 intensity to 0% PDF, okay. And you see the last one from the 255 to the last items. This is a diagonal, and it is very better, okay, smoother, okay, or more smooth. That's right. This is the resultant of an local equalization for improving the histogram. And go to the last slide, maybe. Okay, this is the last slide. Local histogram equalization drawbacks. Okay, is good in all of items? No. Or all of sense? No. What's the drawbacks? Image and is split into smaller regions, and the traditional histogram equalization is applied to each region. Okay, we said this for local. The smaller equalized images are combined into one to obtain a final resultant image. Okay, this is clear. But the final image appears to be very blocky in nature. Okay, here you see this area, and has different contrast levels. This contrast level isn't the same as this contrast level. Okay, you see, for each individual region. That's right. This region with this region isn't the same, and contrast level isn't the same. Okay, why can you do? Okay, what can we do? Post processing may be the key. Post processing is required to remove the blocking artifacts. That's right. Okay, this is the last slide, and maybe the end of the end of the histogram image enhancing. In the next session, maybe we go for a spatial filtering. Okay, spatial filtering, or a spectral filtering. There's any question this time? I name your name, and please one and two. I understand. Mr. Abbas, are you in the class? Mr. Abbas. Ahsan. Please type one. Ahsan. Mr. Ahmed Qasim, are you ready? Mr. Ahmed Qasim. احسنت. میسیز دلال. میسیز دلال تو کلاس هستین؟ شما فارسی بلدین؟ میسیز دلال. میسیز دلال توی کلاس هستین؟ Are you in the class, میسیز دلال؟ احسنت. I know. خب نو میسیز سارا نو. میسیز دنا. میسیز دنا احسنتم. میسیز لمعه. میسیز لمعه احسنتم. میسیز سبا. میسیز سبا احسنتم. حالا میسیز سارا. میسیز سارا was in the class. مستر یاسر احمد. اوکی میسیز سارا. مستر یاسر احمد are in the class. مستر یاسر احمد. مستر یاسر احمد. احسنت. اوکی. مستر یاسر التمیمی. is another one. مستر یاسر احمد التمیمی. Okay. And Mrs. Zainab. That's right. Mrs. Zainab. Mrs. Zainab. Ahsant. Mrs. Zainab is coming with her phone and maybe some delay. That's right. That's right. Very good. Maybe the end of the histogram for our sessions. Okay. And ملتمس به دعایكم. And أقول خدا حافظ. في امان الله. I type in Persian. خدا حافظ. Okay. اور الله يحفظكم. الله يحفظكم. أنا ألتمس بدعائكم. في امان الله. خدا حافظ. مع السلامة. مع السلامة. سلام. اوكي ان شاء الله مسز دلال ان شاء الله. التمس بالدعاء. اوكي. end of recording. stop recording. خدا حافظ همگی.